Ladies and gentlemen, we'll start the session, Accelerating Big Data with LeoFS and Astra. Please welcome Mr. Hara, Mr. Yankit, Mr. Patel. Thank you. At first, let me introduce them. Mr. Yosuke Hara is lead technologist at Rakuten Institute of Technology. He is a chief architect of LeoFS project and a cloud storage shepherd after experience many enterprise systems development. He has been designing and developing LeoFS, which is a cloud storage and a highly available, distributed, eventually consistent storage system. And he has been spending much time on a cloud database project, Astra, from this year. Mr. Yankit Lee is a researcher at Rakuten Institute of Technology. He joined Rakuten on April of this year. He has been in charge of research and development of the cloud storage LeoFS, and mainly focusing on eraser code and NFS support for LeoFS. He will give a part of LeoFS session, which is the eraser code library and NFS v3 support. Mr. Patel is working as DevOps engineer at Rakuten. He is actively involved in the open source project development and support for LeoFS and Roma, which is a distributed key value store implemented by Ruby. His interest area is distributed storage, network, and cloud security. He has completed master course at Mumbai University in India. He is currently developing the Dropbox-like cloud storage for Rakuten internal use, which is known as R Drive. He will talk about one of the use cases of LeoFS. Now, Mr. Hara, please go ahead.
Thank you for introducing me. Hello, everyone. I am Yosuke Hara from Rakuten Institute of Technology. So I have been leading two projects, LeoFS and Astra. We would like to deliver two topics today. First one is LeoFS version 1.0 and the future. Second one is Astra project. It's a distributed SQL database for real-time data analysis. We have been now developing LeoFS 1.4 from this July. There are some powerful features, which are the erasure coding support and NFS support. We would like to cover today. I started LeoFS on September 2009. I was inspired from Google File System, Facebook Haystack, and Amazon S3. I focus on a distributed file storage system, in particular, distributed object storage. At that time, I expected we will face exponentially increasing data in our company in near future. That was the reason why I started Leo project. Let me move first topic, motivation. Our company had managed huge amount unstructured data such as photos, movies, logs, and backup files in many on-premise storages. And we have been surrounded by exponentially increasing data. It's a big data which will reach exabyte in 2020 in our company. We needed to move from on-premise storage to a distributed file storage, LeoFS, more safely, more expensively. If you look at the big idea of LeoFS, what we are really focused on is three important things. First one is high availability. We aim to realize 9 nines operating ratio, which is a very serious figure for us. Actually, to this day, LeoFS keep 100% operating ratio over 4 years. Second one is high cost performance ratio. We are mainly focusing on reduction of storage costs. So we need to realize high performance with minimum resources. Third one is high scalability. We need to huge capacity in order to be able to handle suddenly increasing data and need multi-data center replication for disaster recovery situation. As you can see on this slide, from 1.0 to 1.2, we implemented 3 features. First one is multi-data center replication for disaster recovery to avoid lost data. Second one is NFS version 3 support to easily access LeoFS from your applications. Last one is auto compaction and watchdog feature in order to realize autonomic operation. And now we are working on developing version 1.4, which includes NFS support improvement and implementation of erasure coding feature. From this year, we have been improving LeoFS features, which include multi-data center replication feature and NFS support and others. As I mentioned at former part, we need multi-data center replication for disaster recovery to avoid lost data loss. We implemented data replication between 2 clusters with version 1.2, but now we are planning to implement over 3 clusters replication with version 1.4. In order to keep best condition over LeoFS storage when running it, we are planning to provide the 3 important features from version 1.2 to 1.4. First one is autonomic operation. We provided the watchdog and auto compaction feature with version 1.2 to realize this concept. Second one is erasure coding feature. To reduce disk usage, we have been implementing the erasure coding feature. We are planning it to release it with LeoFS 1.4.0 plus 3, next minor version. This feature will be shared at the latter part. Last one is monitoring tool. In order to easily monitor LeoFS, we will provide the monitoring tool with LeoFS 1.0. LeoFS monitor consists of Grafana, InfluxDB, and Telegraph. As I mentioned at the previous slide, you can easily monitor LeoFS, which includes CPU, monitor, disk, and LeoFS status. Actually, Telegraph plugin for LeoFS was published at InfluxDB's Telegraph repository. You can see on GitHub. So we frequently publish LeoFS benchmark report on GitHub. First, because we shared LeoFS performance to LeoFS users. Actually, many users want to know current LeoFS performance. Second, because we need to check LeoFS performance to avoid performance degradation. You can see many LeoFS benchmark reports on GitHub. Next topic is LeoFS version 1.4 feature, which will be given from Wilson.
So thanks, Hara-san, to talk about the introduction and the roadmap of LeoFS. So as stated in the roadmap, so in 1.4 we have 2 major features. So one is the erasure coding, and the second one would be the NFS support. So let's start. So to begin with, let's recall the mission of LeoFS. So the first mission of LeoFS is to provide data storage with high availability. So that means that LeoFS has to store your data safely in the cluster. So to do it the traditional way, or the way from like Amazon S3, Google File System, or HDFS, what they do is copy a file 3 times. So that means that when you got a file into the system, you copy it and then store it into 3 different locations. So if a node is failed, you can still access your own files from the other 2 surviving nodes. But it costs money because you have to save now 3 times. So it takes 3 times this usage. So here comes the second statement of LeoFS. We want to provide a cost-effective solution. So here, again, comes the magic of erasure coding. So actually what USH coding can do is to keep the same availability level with replication, but at a much lower cost, so even less than half of the storage space. So how it works, so here I will only share a brief description of it. So if you want to know more, check the Wikipedia, actually it's from the informatics. So when you get an object in a USH coding system, you would do some computation on it. So this process is called encoding because you will create some extra redundancy and, in other words, some protection of the original file. So together with the original file, they will be divided into smaller units. So that's what we call encoded objects. And then similarly, we distribute in multiple locations. So similarly again, if a node is failed, you can still get your original file by first retrieving the surviving those available blocks, and then do a computation. So this time is the decoding and get the original object back. So to summarize it, so USH coding can save this space by doing some computation on it. Actually, LeoFS is planning to support both replication and USH coding together at the same time and let the user choose which way to go, like this data I want replication, or maybe the next data I want USH coding. But why? It's because actually these two schemes have their different purpose or maybe different focus. So that means they will have their different benefits, but at the same time, they will have different price to pay. To elaborate on it, to start with replication. So replication is very straightforward. You write and read, just write multiple copies. So read any mirror, you can read it. So the management and recovery is very trivial. So if some mirror is missing, copy from others. So if you want to focus on our performance, replication is the way to go. But you have to pay the price. So you have to pay the money to store multiple copies. So compare it with USH coding. As I said, USH coding can save the storage costs by reducing the disk usage to half. The downside of USH coding is now in write and read, you have to do some computation. So encoding on read and then decoding during read. Encoding during write and decoding during read. So this computation would add a bit latency to it. So the performance would be lower compared with replications, and the management and the recovery would not as trivial as replication. But don't worry with that, LeoFS will handle it for you. So that's about USH coding. And the second feature we want to add in 1.4 is the NFS support. In particular, we want to improve it. So the way why we want to add NFS to LeoFS, we want to push LeoFS as a data hub of operations. So LeoFS starts as an S3 compatible data storage. That means that you can easily host your web service or web page on it by storing your documents, contents through HTTP protocol into LeoFS. But now we are in the age of big data. We are not only care about the huge amount of data we want to store, we actually want to dig out the huge value from those data. So to facilitate this process, to provide convenient way for programmers and data scientists to do the analysis, we provide NFS support to them. So they can use a mount point, so they can work as on the local file system, so which is very convenient to them, and they will be happy, I would say. So to improve NFS support, like from 1.1, version 1.1, it actually have NFS support already, but at that time, we tested with Linux client. So in particular, 1.4 will test it with FreeBSD client too. So the second task of improving the NFS support is to improve its performance. So here we share just a small benchmark or test case, so which is what we call the LS test. So the test case is quite simple. So you have a directory tree with multiple directories and then a huge amount of files in it. So the task you want to complete here is you want to retrieve the whole list of metadata for all the files under the directory tree. So here is the benchmark chart, the result. So y-axis is the total duration it took to complete the whole process. The x-axis we categorized into 5 test cases. So from 500 objects to 10,000 objects. So in each test case, you can group it into 2. So the first group or maybe the first two, which are much lower, much shorter. That means they are much faster, they are much better. Of course, they're the new version, 1.4. So and then the second group, it takes actually 5 times more time to complete the whole process, is from 1.2. So if we compare 1.2 and 1.4, actually in 1.4, it takes less than 20% of the time to complete the same process. So we are still still on the process to improve the performance and improve the compatibility, and we keep pushing our benchmark report into GitHub. So please track it. So now I will pass on to Paris, and he will talk about use case in Rakuten.
Hello, good afternoon. My name is Paras, and today I'm going to talk about use case of LeoFS at Rakuten. How we utilize the LeoFS at Rakuten. A Rakuten standard storage platform, which is known as a R drive. R drive is a combination of LeoFS, OpenCloud, and some other open source technologies like Roma, MariaDB, Nagios, Ganglia. Target behind this platform to reduce the cost, to handle the strictly confidential files inside the organization, to store large amount of and large size of files, and scale this cluster very easily. Usage: we store the documents, videos with the group of companies, and inside the 20 companies, over 10 countries and continentals. Over 10,000 users and over 4,000 teams use this platform. System layout of the R drive. In the core of the R drive, we are using LeoFS to store the data in our data centers. For the web-based user interface, we use open source platform OpenCloud. To connect OpenCloud to LeoFS, we use Amazon S3 protocol. To store the metadata information of the whatever objects, files, we use MariaDB. To store the search session, login session, we use Roma, which is also one key value store developed by RIT. And the authentication module, we use LDAP. Behind this, we are also using several technologies like MariaDB, Kibana, Capistrano, Ceph, Elasticsearch, Vagrant, etc. R drive data is stored inside the Rakuten data center. So what does it benefit? Our data is secure because it is in our data center. We have 100% ownership of our data. Data access is very fast because all the subsidiaries are connected with these data centers with leased-line. Data center VM, which are running the applications, they have a direct access to this R drive. They can access data, get or put using wget or webdev, any of the webdev client. Data sharing is so easy within the organization. You can share data just by searching the intra-user name. You can use mailing list. You can create your files hyperlink and share with your colleagues. You can set the custom permissions, read, write, delete, etc. Even you can set the password for the strictly confidential documents and expiry date of that particular link. R drive having some engineering features, which definitely engineer will like it. WebDev client like Cadaver, DevFS 2. You can use this client using WebDev protocol to access your data. If you don't want to use web interface, then just you can use desktop sync client. You will put everything behind the duties of the desktop sync client. It will sync automatically in the background. Even you can use wget, curl, and API access to access your data from R drive. We are currently working on mobile applications, and even you can mount R drive as a network drive. And also, it having some file sharing and file system basic features, like you can create, upload, download the files. You can view the pictures, read PDF, watch videos, even delete and restore the files, and automatic versioning of the files. Whenever you delete or restore file or making the versions, so your quota or your deleted data maintain automatically time-based and quota size-based authentication. Even you can mark as a favorite files, bookmarks, and we use Confluence for documentation. Whatever video you can upload on the R drive, you can embed in the Confluence pages. Our aim is to spread this service along 25 countries and regions, or more than 20,000 users to give this service. That's all from my part.
So next topic is future plan. So we have been aiming to deliver LeoFS 2.0 at latter of 2016. I'd like to share the future of LeoFS 2.0 briefly. There are four things of the new feature of 2.0. First one is layered storage. In order to more efficiently manage files, we are considering LeoFS store cold data and hot data separately. Second one is data deduplication. In order to more reduce disk usage, we will implement this feature. Third one is NFS V4 support. There are benefits because it's an industry standard file access protocol. Last one is QoS, quality of services. This feature is able to control user access to keep best condition of LeoFS. Wrap up LeoFS segment. We aim to realize three important things for LeoFS. First one is cost-effective, reliable, multi-DC replicated storage. Second one is utilizing LeoFS for cloud computing and big data. Last one is in order to easily operate LeoFS, we have been delivering LeoFS tools. This is the end of LeoFS segment. The next is Astra segment. We started Astra project last September. We are focusing on delivering a real-time data analysis database. There are three topics I'd like to cover today. First one is vision and concept. Second one is architecture overview. Last one is current works and future plans. Let's move first topics, vision and concept. What we are really focused on is collecting, analyzing, aggregating big data to find values in real time at low cost. Values mean trend, forecast, unexpected data, and others. There are two ways of collecting big data. First one is batch processing. Original data is stored into LeoFS at once. Then it is parsed and optimized when putting it into Astra. Second one is stream processing. A parsed and optimized data is stored Astra directly by a stream processing system or any applications. Astra is able to aggregate and analyze big data by ad hoc query, and you can use third-party BI tools to visualize the result. So we are focusing on accelerating big data with LeoFS and Astra more easily, more efficiently, more sophisticatedly. Astra is a scalable, multi-DC replicated, and transactional SQL database for real-time analysis. Astra supports pure SQL and implements the SQL engine to be able to easily connect Astra via ODBC, JDBC clients. And Astra is able to communicate with machine learning library on the distributed computing feature. And also, it is able to communicate with LeoFS to collect unstructured data, manage models and feature vector for the machine learning feature, and manage backup files. So Big Data Accelerator consists of LeoFS and Astra. There are 5 phases in the processing flow: collecting, parsing and loading, aggregating, analyzing, and visualizing data. Firstly, a client collects original data with NFS or S3 API. Then LeoFS trigger passes and puts data to Astra. Or stream processing or any applications directly stores parsed data to Astra. Then Astra aggregates data with the SQL engine and the distributed computing feature by an ad hoc query. Finally, you can visualize data with BI tools and dashboards. So we support 5 phases with LeoFS and Astra. So as you can see on this slide, you can understand the position of Astra and LeoFS. Astra is a scalable multi-DC replicated transactional SQL database and also deliver real-time data analysis feature. On the other hand, LeoFS, which is an unstructured data. Astra supports pure SQL. There are many benefits for users because Astra is able to easily communicate with your application and third-party tools via ODBC and JDBC. There are many BI tools such as Dundas BI, Tableau, and QuickSense. Wrap up a first topic of Astra concept. Astra is a distributed SQL database for real-time analysis, which includes the distributed computing feature and machine learning feature. What we are really focusing on is collecting, analyzing, and aggregating big data to find values in real time at low cost, and more efficiently and more sophisticatedly. Next topic is architecture overview. Astra consists of 4 core components: Astra Gate, Astra Base, Astra ML, and Astra Manager. A client requests a query via ODBC or JDBC or a protocol buffer over HTTP or Astra's data transporter, which supports CSV, JSON, Excel, and other formats. Astra Gate, which handles requests from client with the SQL engine or Astra's protocol buffer. And Astra Gate supports built-in data cache mechanism in order to keep low latency. Next one is Astra Base, which stores and manages records into an Astra Base cluster. Records are replicated and repaired automatically. Next one is Astra ML, which consists of the distributed computing and machine learning feature. We are now considering Astra ML communicate with Spark machine learning library and Google TensorFlow. Last one is Astra Manager, which always monitors all of Astra Gate, Astra Base, and Astra ML nodes in order to keep running Astra. Also deliver Astra command to easily operate Astra. We adapted nested data model. Each column has a data type, such as integer, float, long, date, string, and structure. Also has constraint in order to be able to strictly validate all of records. Astra supports both nested data model and flat data model, which includes protocol buffer and JSON object as nested data, and also CSV, TSV, Excel, and other formats as flat data. Astra implements the hybrid-oriented table, both row-oriented table and column-oriented table, because in order to realize retrieving records faster, Astra needs to access row table or column table properly by a query feature. Astra creates a query plan by the SQL engine, then executes the generated query in parallel. And retrieved records are stored into the data cache in order to reuse them. So Astra is distributed SQL database, not NoSQL, and of course supports pure SQL to communicate with any client smoothly. As with other databases, Astra SQL implements SQL Analyzer, SQL Optimizer, SQL Planner, and Query Cache feature. So we are now concentrating on delivering a real-time analysis database. So we have been taking many benchmarks of Astra's SQL parser to recognize its performance. As you can see on this slide, we took benchmark of 3 cases. Simple query was taken on 8-core server. Complex query was taken on 8-core server, and a complex query was taken on 16-core server. Maximum operation per second is 175,000, and minimum mean latency is 0.16 milliseconds. It is good result for us. The detail is like this: first case, second case, and third case. So next topic is strategy of data distribution. So in order to rapidly retrieve raw value, column value, and metadata, each value is assigned suitably into an Astra-based cluster. Each group depends on a table schema. There is a simple rule. In order to easily and rapidly retrieve same group values, a child element is same group as the parent. For example, regarding group 2, links.forward and links.backward, which are assigned at the same group. Astra has a transaction mechanism and a transaction control with the consistency manager and transaction manager. Astra gets requests retrieving, inserting, updating, and removing record to Astra-based cluster. Then, a primary node of Astra-base starts a transaction when executing put, update, deleting operation. In order to realize lock-free transaction, every record has a version values. Astra adapted multi-version concurrency control, which is called MVCC. Also, Astra supports serializable snapshot isolation and snapshot isolation. Also, Astra consensus algorithm is based on Raft, which was published by Stanford University. This slide is the data structure of Astra. As you can see on this slide, there are 4 kinds of tables. First one is version control, which manages current version of a table and column in order to carry out a lock-free transaction. Second one is index table, which manages primary key of a row record. Third one is row table, which manages a column value atomically. Last one is column table, which manages a column value atomically, which is similar to row table, but it consists of metadata of column value and container of column value. Many column values are stacked into the container in order to reduce disk usage. And also, Astra keep consistency between row table and column table. Next topic is distributed computing feature. Astra executes a job which is using built-in functions, UDF and UDFS, with or without machine learning feature on a distributed computing cluster. A job is divided into a plural tasks, and then the manager nodes are tracking them and distributing plural tasks to Astra ML worker nodes. Finally, all of tasks are executed in parallel. Retrieved data by the worker node is stored into the data cache in order to reuse them. There are many built-in functions aggregating, collecting date and time functions, and others. We aim to deliver easily writing UDF and UDF with this feature. So last topic is current work and future plans. So we are now working on the first phase, mainly concentrate on the implementation of SQL engine and implementation of core component, which includes replicator, repairer, and transactional features. In the second phase, we are planning to implement the distributed computing component to be able to aggregate values and machine learning feature. We will support communication with Spark machine learning library and Google TensorFlow. So we release Astra base beta 2 to Rakuten in-house. After that, we will need to fix many bugs. So finally, Astra will be published as open source software at summer of 2016. In the third phase, after release Astra as an open source software, we may get many feedbacks. We will make a plan of the third phase by many feedbacks. Again, what we are really focused on is collecting, analyzing, aggregating big data to find values in real time at low cost. So we are focusing on accelerating big data analysis with LeoFS and Astra more easily, more efficiently, and more sophisticatedly. Again, Astra will be released as open software at summer of 2016. But we need to overcome a lot of obstacles by that time. So this is the end of our presentation. Do you have any questions?
If you have any question, please raise your hand.
Hello. Yeah, I have a question about R drive. So this R drive is only for Rakuten internal employees, or external employees, external people can also use R drive?
Yeah, all the intra-user of the Rakuten, they can use R drive, including all subsidiaries in other companies also, other countries also.
Okay. Do you have any plan for external people also, like Dropbox or something like that?
No, currently we don't have that kind of plan. Currently we are building this platform for Rakuten only. Thanks.
Thank you.
So regarding this Astra, you mentioned that it's it's more sophisticated approach for data analytics in real time. I guess that comes from the fact that you achieved 175,000 operations per second on some of your tests. So was that using off-the-shelf hardware, or was that some specific SSD-based array or something like that?
Yes. So we are planning to use SSD with Astra. So not hard disk drive. So because
IOPS, I guess.
yes.
Okay, so that's fine. So that's clear that it's off-the-shelf hardware with SSDs, probably, right? That LeoFS will use in order to run this data structure.
So sorry, one more.
So I guess it will be off-the-shelf hardware with SSD arrays for LeoFS file system.
No. So we recommend so you use a hard disk drive with LeoFS, but Astra you use SSD.
I see. So there is a differentiator there. So for
Yes.
LeoFS, you're looking for the sort of cold data, whereas Astra, you're looking at the hot data. Is that a differentiator?
Actually, we are using LeoFS as image hot storage and backup storage. So We are both hot data and cold data, so we handle both
Okay.
with LeoFS.
Okay, so last question. In my work, we have highly hierarchical data structures. And we are challenged using key value pair approach for those, because if you have a very deep hierarchy in your data structure, you have a lot of losses as a result of having to relate to the parent node every time. Do you find Astra can tackle this kind of challenge efficiently?
Yes. So, yes. So we are now considering, so Astra has two oriented tables. First one is row table and column table. So data is assigned as suitable tables, row table or column table. So now we are using RocksDB, but now we are customize RocksDB because we are able to solve. So we are now building column table in RocksDB. So you are able to more. You are able to get more performance. So we will provide customized RocksDB for open source software.
Okay, thank you very much. That's very interesting.
Sorry.
So it seems like you are supporting my question in two questions. So it seems like you are supporting relational data models. Is that true on the Astra? And second question is, where is your the Astra stands for the cap theory? Is it CA or AP or CP? That's two questions.
So sorry. So I don't.
First question is are you supporting relational data model? Relational data models.
Relational
data model. So like the traditional database, you can have relationship between.
relationship. Sorry.
RDBMS みたいなリレーショナルデータモデルをサポートしているか。
Yes. So we will support relational models. So which is third phase. Inner join and outer join will support this feature.
Okay.
And
Thank you.
second question.
The second question is your database is a CP or consistency or cap theory?
Yes.
Which is where is your database stands for?
Eventual consistency. So AP.
AP.
Yes.
Okay.
But Astra has implements transactional feature. Yes. But keep consistency is very difficult for us. So we are now considering so strictly keep consistency.
Strong consistency.
Yes.
Okay. Thank you.